Okay, part two. All right. So, uh, the one, the one thing I think a tip for everybody is if they want to ever find out what hardware they are running on their computer, is just do LSPCI, and it's gonna show you like all the like PCI cards and NVMe and all the little I/O things that's connected to your computer if you're running Linux. Um, so my computer is very basic. I'm just off of a mini PC. I screwed up my desktop a few weeks ago. Haven't gotten it back up since, but that's okay. Um, and uh, yeah, I have a Thunderbolt port, and I'm very disappointed because um, I wanted to hook up an external GPU. It just crashes this computer. I have no idea why. Um, it was funny because this specific computer, this install of the specific installation of Ubuntu was it did have an NVIDIA card. I mean, it was the same card in that computer. So um, yeah, so odd. Anyway, okay, so um, basically what I want to do is I know it's painful to watch me struggle, and although I'm very grateful for the 300 whatever subscribers I have watching these videos. Unfortunately, I don't think there's enough people to help me out live, right? When I get into these situations, and I don't really think it's useful to watch me struggle for like, I mean, it's good to watch me struggle, but not for like 10, 15 minutes at a time. And it's not good use of everybody's time, especially since I do know that people are learning from these videos. So, yeah, yeah. I would rather have I would have you guys watch me struggle on like algorithm stuff, like real programming problems, as opposed to like, oh, I don't know how to include something. So, um, I think it'll be helpful, especially since like the internet is so filthy in terms of like search results nowadays. Like for example, you go to google.com and you're like, get ADR info. Like you just get a bunch of like stuff, right? So, okay, maybe this is pretty good, but um, I would rather have like some quicker way, maybe. I don't know, but it's also like good experiment to have this LLM here that will answer some of the basic questions. Maybe I don't know. I hope it's good. All right, so basically, I use something called Olama. All right, it's a it's a platform to get local LLMs going. So it's a very easy way. It supports Linux and Mac OS, and I guess to a certain extent Windows. But I think for Windows you can just get away with installing the Linux version on WSL. So it's easy. It's just a shell script. You just do this. Um, you just basically curl install, and it installs Olama as a service, pretty much. Oops. Okay. I don't know why I can't get my password right. Silly. Oh, it's there. Okay. So I'm on a slower connection. So this might be a while. But anyway, while that is going, um, there's a few local models that you can use with it. So it's kind of like your mini chat GPT inside your own local computer. And if I feel like it's better for like privacy and all that stuff, especially like, you don't know what OpenAI and all the other companies are doing with all the messages that you send them. So, for those who are not familiar, like these models are basically the AI, the thing that you talk to. Olama is just kind of like the interface, like the basic interface that you interact with. So and it's also a good it provides like an API so you can actually program against it, and maybe we'll do that in the future. But yeah, so you have these like models here that you can actually load into Olama and start chatting or even developing against. Because some of these models, if it has tools right here, you can actually tell it like to run specific scripts locally on your computer. It's really cool stuff actually if you really know how to like use it. Like I actually personally have not used it as like a chatbot extensively. I've used it as a way to automate my things by invoking tools. And I think the natural language processing of these AIs are actually the more powerful thing about them, as opposed to like the chatting aspect of it, like chatting like a real human or the text generation. I think they're very, very good when it comes to natural language processing because they can understand you, and then based off of that, you can, they will invoke those tools. So basically, you have these models here that have been created by various companies. You have Meta's Llama 3.2, which is like a smaller model that is meant to be very good for a small model. So when it comes to model size, right? Basically, how it works is every model has a number of parameters. So if you really think of like a model as like a math equation, think of it like as in I'm sorry, people are gonna like really hate me for explaining it this way, but think of it as the number of like equate like the terms in an equation that you have. Like, basically, the more parameters you have, the more you can compute different like things, right? Or like you don't lose as much information, basically. Um, so a 1 billion parameter model is not going to perform as well as a 3 billion parameter model, right? And it's definitely not going to be as good as a 70 billion or even a 405 billion parameter model. So let's just take Llama 3.1, for example, just an example. Okay. So we have various model sizes here. You have an 8 billion one, a 70 billion one, and a 405 billion parameter model. Now, notice the file size here. So as you scale up in the number of parameters of a LLM, what ends up happening is that you need more space in your disk. But not only your disk, if you're actually running these models on a GPU, for example, you need to have pretty much this much VRAM at least, right, in order to actually load and run them effectively. If you try to load a model that is quite big for the amount of VRAM you have, you're just going to get very slow processing. So if you ask it like a question, it'll just like output like one word at a time. And you'll see what I mean if I ever get this downloaded in time. Um, so that's one thing, right? Um, so you have to based off of like what you choose, it's going to really determine the performance of the model on your local computer. Now, if you have a GPU, that's great. Select the model that will likely fit in your GPU memory. So, for example, if I had my 3060 Ti working, I would have gone for a 8 billion parameter model. But that's like not the end of the story. This is like just partially, right? You have an 8 billion parameter model, it's 4.7 gigabytes, but you notice how there's this thing called a quantization here. This quantization Q40. What does that mean? Well, if we take a look at this by expanding, pretty much going back to here and saying view all, for example, you'll have various types of um, uh, very like variations of the same model, right? So let's go to 8 billion for example. Let's go all the way to 8 billion. You'll have something called 8B instruct, and then you have something called 8B text. Now the 8B text is specialized. These models are specialized for generating text, not really chatting, but like pretty much like an autocomplete style. Whereas these instruct type models are geared towards chatting. So understanding the user input and then responding accordingly based off of some context. Now, when it comes to this quantization thing, remember we saw it was like Q40. I think that's like the number of bits each parameter can take in on average, right? So the higher basically your quantization, the more bits you can represent in a specific uh, parameter, the more detailed the result will be, and thus the more accurate or accurate, but like the higher quality the model is going to be, and less stupid, for instance. So here's FP16. Think of that as like two bytes, right, per um, parameter. And that makes sense because you have 8 billion parameters, right? 8 billion parameters. So that's, if you're thinking about it in terms of numbers, right? 2 bytes per number, 2 times 8 billion is about 16 billion bytes. Okay, and that's about 16 gigabytes. So it's expected. This is, we can think about, in this world as an uncompressed model most of the time, just for simplification. Now, if you're really strapped for VRAM, for example, you can actually go 8 billion parameters, but also choose a quantization that is much smaller. Basically, let's say here, Q2K most likely means that each parameter is going to be 2 bits. Right? So we actually compute that. It's essentially about the right size here. So 2 bits is going to be like a quarter of a byte, right? So a quarter, 0.25 times 8, it's about that much. So we have 3 bits, and I don't know what KLKM are, so it's not a concern for me, but that's the pattern that you're going to see in these types of models that you download. Okay? All right. So I don't want to download something big right now because that's going to take a long time for me to demo. I'm going to download something small. I'm going to download Llama 3.2, which is a very new one from Meta. It has 1 billion parameters. Okay. And that is going to be 1.3 gigs. And it's a quantized 8 bits per parameter model. And that's usually like the normal. I think, you know what, before I start talking away, I'm going to just download this. So you recopy this command here with the 1 billion. I'm just use the Q80. I'm going to just paste that in here. And it's going to automatically start downloading the model. Okay, now I can talk. All right, so I think Q8 is 1 byte, right, per parameter. And so that's why it's close to pretty much 1.3 gigs. Okay, so you know how we have like tops, right? In AI, there's like AI tops. Like that's like the new benchmark to measure like NPU and all that stuff, right? Like these new accelerators that is like, oh, it is 100 tops, or it's like 50 tops, or whatever. So what is tops? Tops in this case is let me try to find it. Oh, come on. See, this is the reason why. Okay. Come on. Tops. Define tops for me. Tops. 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 Okay. So tera operations per second. It's the number of operations like in I think trillions, right? That is based off of how many, I think, operations in the sense of correct me if I'm wrong, anybody who's an expert, 1 byte. Those 8-bit operations, those 8-bit parameter operations. So tops measurement. Trillions, yeah, trillions, tera operations. Let's see. What is it based off of? Quantization. Come on. Qualcomm, don't fail me. My internet, it's like desaturated. Okay. AI tops. Okay, the heart of NPU, tops quantifies, okay, addition. So the number of operations, additions, the multiplies, all these operations, because really when you do right here, okay. Let me just first of all back up a little bit. So whenever you execute a model, whenever you run some sort of query against an LLM, what you're doing is what we're calling inferencing. So in AI, there's like two things to it. One is called the learning or training aspect of it. That's like the machine learning, where it's actually trying to create the model. You're building the model, right? Once you have the model, like what we're downloading right now, the way you use it is by inference. And when you inference something, when you inference a model, you're pretty much forcing it to do a bunch of computation in order to get what you want. Now, in the sense of AI, like what we're most interested in, if as consumers, is the inferencing part of it. And how we measure the performance of inference is going to be through this TOPS thing. Okay, and TOPS is okay. So the current industry standard for measuring AI inference in TOPS is an int8 precision. So integer 8. So that's the Q8 underscore 0 that we're seeing in Olama right here. So uh, yeah, that's it. That's like the basic overview of uh, a local, how to get started running a local model. If you're on Linux, it's very easy. Just run the shell script, and then it's going to install the Olama uh, service. See how it says NVIDIA GPU installed, because I actually had the drivers, but then whatever, I don't have it plugged in because something's wrong. So after that, you pick a model you want, you download it. I would rather go for like more recent models. So if you kind of just search for models here and you filter by newest, for example, you'll get a bunch of these. So I picked Meta's Llama 2.2. It's rather good. I've been wanting to also try IBM's new model, Granite, um, but haven't had time yet. But let's just see how this one performs. And we're actually going to use this through CPU, purely CPU. So if you have an AMD card, you need something called Rock M, which is probably only available in higher end SKUs. So let's check it out. So let's do Olama GPU support. So this documentation on Olama's GitHub repo will actually show you the supported GPUs and for AMD and NVIDIA. Apple is fine. Apple will use the Metal API, and of course, Apple. But if you have an NVIDIA GPU, you can pretty much go all the way down to the 750 Ti, and that's like a really old card, assuming your model can fit. And yeah, Rock M, notice how that for Radeons, it's going to be a little higher end. Yeah, but I personally have 3060 Ti. Where am I? Oh, right here, this one. So it's pretty high up there for inferencing. Um, yeah, so this one has like an integrated Intel GPU, so it's going to be very slow. It's just going to purely use CPU. So the thing with inferencing is that if you don't have a GPU, it's going to tap into your CPU, and how it loads the model is going to be all through RAM. And just for anybody who are not aware, the memory bandwidth of GPU is much higher than the memory bandwidth of the RAM on your CPU, near your CPU, motherboard, whatever you call it. So that's the reason why LLMs tend to perform much faster, aside from all the tensor calculations, the matrix operations on your GPU. Just shifting and moving that data around is tremendously faster on a GPU as opposed to the CPU. Okay, so we've loaded the model. Now let's just say hi. Hi there. Hi, how can I help you? Hey, it's not too bad. It's pretty fast actually for CPU. Um, and just so that we can monitor the intensity, right? Well, we can do a system monitor, and we can actually just see how it's working. So let's ask it our get ADDR problem. Let me just minimize that. Okay, so um, it's like I am having a problem with my C program. I cannot seem to include get ADDR info. It's yeah, just see. So you'll see that here the CPU activity is spiking. Okay, and yeah, we've loaded the model into memory. It's not a big model, so it's why you don't see a difference. But yeah, so the get ADDR info function is part of the POSIX standard and is typically used for network operations on Unix-like systems. Have you checked your system's error messages? It's possible there's specific requirements or restrictions. Okay, what is your style? Are you okay? Okay, so this is good. This LLM is not confidently wrong. It's actually trying to help us, right? So I'm gonna say, yes, I have included the necessary headers like netdb.h and syssocket.h. So okay, libc or unistd headers. However, there's an equivalent in the C standard that provides similar host information. Okay, so we could use the get host by name function from the libnet db.so. Okay, so here's like an alternative. I'm not gonna really try it, but um, yeah. Actually, you know what? Let's do this real quick. Let's do that. Let's actually just copy paste and then let's see. Let's run it and see if we can get our Wikipedia working. Let's see if it actually did anything. Okay, this computer is starting to really mess up. All right, so let's do it real quick. Let's just paste that in. Okay, and then instead we'll do wikipedia.org. Okay, and then we'll save that in. Let's just save it for. Let's save it as wiki.c. Let's just save it at the same place. Okay, now I'm going to do Control B C to create another pane. I'm gonna do code average def projects C. What was I? HTTP client. Oh, what is this? Host and has no field. Oh my god. Okay, so maybe this LLM is having an error. Blocking host host and host address is what? This one? A list of addresses from the name server. Oh, okay. So it's changed to have a list of addresses. Okay, let's find the base one. The base it's a 2D, not 2D. It's a double pointer. So we'll just have the first base one. Okay, so let's do wiki.c. Okay, warning. That's fine. It's p close. Okay, weird. Okay, a.out. Okay, so probably not the best, but it got us. It's getting us somewhere. Maybe I'm just doing it wrong. Can I do something like dereference that? I don't know. Okay, well, it got us there mostly. We can just kind of say how to. Okay, oh, this is actually interesting. Now I think what's useful is now we can search, right? So now we can actually man host and or actually get host by name. Get host by name. And this is where we can actually go deeper. I think this is where this is useful at least. So maybe this is too much. So we can probably do something like google.com, print out the host address from get host by name. So extracting IP data. Ugh, okay. So if we do this, we'll have this one here. And I guess there is a process to actually get the list of addresses. So I'm tempted to just do this. So bcopy inet. Okay, so let's just do this. Let's just copy this. So it's helping us. This LLM at least gave us a hint, right? So I think that's not too bad. We'll just need to kind of do host int or host. Okay, and this will be host. And this one is going to be, what is this? This one is, what is A? What is A? Oh, in ADDRA, okay. So, struct in ADDRA, okay. And that is going to be readily available. Okay, so maybe this is better. Let's see. Probably need to include something. ARPA. B copy. Okay, we need B copy too. I'm guessing this is in string.h. Taking guesses. We're here to have fun. Okay, so be a infinite loop. Okay, so this is supposed to work. Guess not. Oh, success. Okay, I don't know what that means though. Get host by name. Get host by name success. Where did we print that? Get host by name. Let's try it again. Get host by name success. Oh, I think it's just the P error thing. Get host by name, and then we print out the error. Okay. All right. Well, we got most of the way there with the LLM, and that's the reason why I think the lesson here is that LLMs are just there to help hint for you and not actually do your stuff for you. So I was not aware of this get host by name. So at least if I had more time here, I would totally look into that. But I only found that out by asking. I mean, I could have searched more and more, but I found it quicker by just talking to this guy, right? So then this is it. How do I print the list of IP addresses returned by get host by? Let's do that. So yeah, and I advise not to rely too much on this because it could be wrong, like just now. So okay, so it is just doing this. Oh, that's too much for now. We'll try it. We'll try it. And what do we need to include here? We got everything. SA data, ADDR is going to be what? Let's do it. SA data. So another LM fail, but we're on a 1 billion parameter model, so give me some credit. Let's see. So I'm guessing I didn't. Let's see, ADDR. Where's ADDR? Where is it actually being declared here? Right here in ADDR. So. It says what's the error? Has no field SA data. Is it because we have to cast it? Let's see. Struct in ADDR. Did that help? Nope. Getting struct ADDR has no field SA data. Let's see what its response is. Incorrect. Oh, it actually contains an HADDR list array. Okay, try again. See what happens. Still wrong. Because this is going to give us an error. Okay, well, can you at least write me a poem about the struggles of C programming? Let's do that. In realms of code where errors roam, a warrior battles alone and home. A cursor blazes like a fiery flame as syntax rules are cast aside in vain. They include directive, a treasure rare, is sought with zeal but often left to share. The semicolon silence, a deafening sound. Okay, they're too long, but not bad. It can generate poems, but that's about it, right? Actually, yeah, this is what I meant by LLMs aren't really good for this like I think they're okay. It helps you out with getting started on things, but really, you see how like we tried to use it to solve a problem. It didn't really help us much, but yeah, these got us started in looking in the right direction. Um, and again, like these smaller models are very helpful in terms of the natural language processing, not really like the chatting aspect of it. So yeah, just this is I don't know. I'm just installing it right now, hoping that this will actually help us better in the future. And maybe I'll use it, maybe I'll not. Just wanted to kind of show you guys like a little bit of what these local LLMs are. You can take my advice. You can just ignore me. But yeah, I hope you learned something. And this is remember this is like a 1 billion parameter model, so it's actually pretty good for only 1 GB. So it's actually what you would see built into some of these new computers that are coming out nowadays. So yeah, see you tomorrow.